I greet you on the QUASARIA channel. Today we will immerse ourselves in one of the most exciting and frightening scenarios that the human mind can imagine. What will happen if our home planet Earth finds itself near a black hole? This question haunts scientists, science fiction writers, and everyone who has ever looked at the starry sky and wondered how fragile our existence in the universe is. Black holes are some of the most mysterious, powerful, and destructive objects in space. They are so dense and possess such incredible gravity that even light, the fastest thing in the universe, cannot escape from their tenacious embrace. But what will happen to our planet, to us, to everything we know and love, if we find ourselves too close to such a cosmic monster? Prepare for a journey through space and time, where physics becomes strange, the laws of nature reach their limits, and reality turns into something unimaginable. Don't forget to subscribe to the QUASARIA channel and put a like if you're interested in this topic. Turn on the notification bell so you don't miss our new exciting videos about space and its mysteries. And now fasten your seatbelts. We're setting off on a journey to the very edge of the abyss. Before we send Earth toward its possible doom, let's figure out what exactly we're dealing with. What is a black hole? It's not just a hole in space, as one might think from the name. A black hole is a region of space-time with such powerful gravity that nothing, absolutely nothing, can leave it after crossing a certain boundary. How are these cosmic monsters formed? Most black holes are formed when a massive star, tens of times heavier than our sun, exhausts its nuclear fuel. For millions or billions of years, a star maintains a balance between gravity trying to compress it and the pressure of thermonuclear reactions trying to expand it. But when the fuel runs out, this balance is disrupted. The outer layers of the star explode in a catastrophic flash called a supernova, one of the brightest events in the universe. And the star's core collapses under the action of its own gravity. It compresses more and more until it reaches such density that even atoms are destroyed. Matter continues to compress until what physicists call a singularity is formed, a point in space-time where density becomes infinite. Imagine an object that compresses mass exceeding the mass of our sun into a space the size of a city or even smaller. Some black holes have a mass of tens of suns compressed into an area of just a few kilometers. The density of such an object simply defies imagination. If you took a teaspoon of matter from a black hole, it would weigh billions of tons. Around the singularity exists an invisible boundary that scientists call the event horizon. This is the point of no return, the final boundary. Once anything, whether a spaceship, a photon of light, or even information, crosses the event horizon, it is doomed to fall into the singularity. No force in the universe, no technology, no laws of physics can save an object that has crossed this boundary. The size of the event horizon depends on the mass of the black hole. For a black hole with the mass of our sun, the radius of the event horizon would be only about 3 kilometers. This is called the Schwarzschild radius, named after the German physicist who first calculated this value. There are different types of black holes, and this is important for our scenario. Stellar black holes are formed from collapsing stars and have a mass from 3 to several tens of solar masses. These are the most common black holes in our galaxy, and there may be millions of them. Then there are supermassive black holes, which are located in the centers of virtually all large galaxies, including our Milky Way. These giants can be millions or even billions of times more massive than the Sun. The black hole at the center of our galaxy, known as Sagittarius A-, has a mass of about 4 million suns. There are also intermediate black holes with masses from hundreds to thousands of solar masses, although they are rarer and less well studied. And finally, there are theoretical primordial black holes that could have formed in the first moments after the Big Bang from density fluctuations of matter. For our scenario, let's consider a stellar black hole with a mass of about 10 solar masses, a fairly typical representative of its class. This is a medium-sized black hole, not too small and not gigantic. Its event horizon would have a radius of about 30 kilometers. It's important to understand that black holes don't suck in everything around them like a cosmic vacuum cleaner. At large distances, their gravity acts exactly the same as the gravity of any other object of the same mass. If our sun suddenly turned into a black hole of the same mass, which, by the way, cannot happen since the sun is not massive enough, Earth's orbit would not change. We would continue to revolve around it at the same distance. The danger of black holes manifests when you find yourself too close to them. That's where gravitational effects become extreme and truly strange things begin to happen. Now that we understand the nature of our adversary, let's see what will happen when Earth begins its fateful journey to this cosmic predator. So, let's imagine an incredible scenario. Somehow, perhaps due to gravitational disturbance from a passing star or some other cosmic cataclysm, our Earth was knocked out of its comfortable orbit around the Sun. It began to drift in space, and its trajectory, by unfortunate coincidence, leads directly to a black hole. When will we first realize we're in danger? When would the first signs appear that something terrible is approaching? Assuming Earth began movement from the periphery of our solar system in the direction of a black hole located at a distance of several light years, the first signs would appear long before we approached the black hole itself. Astronomers would be the first to sound the alarm. Black holes themselves are invisible. They don't emit light, but they manifest themselves through their gravitational influence on surrounding space. The first alarming signal would be a change in the starry sky. Astronomers would notice a strange region of space where stars behave unusually. Their light is distorted. They change position or disappear. This phenomenon is called gravitational lensing. A massive object, such as a black hole, curves space-time around itself, and this curvature bends the trajectories of light rays passing nearby. As a result, we see distorted, multiple, or magnified images of distant stars and galaxies. As Earth continued its movement, this strange region of space would become larger and more noticeable. At the center, an absolutely black area would form, the shadow of the black hole. Around it, we would see a ring of light formed by photons orbiting the black hole. This phenomenon was first photographed by astronomers in 2019 when the first real image of a black hole in galaxy M87 was obtained. But visual effects would be the least of our problems. As we approached, at a distance of approximately several million kilometers from the black hole, its gravitational influence would begin to become physically tangible. The first victim would be our moon. The moon is held in orbit around Earth thanks to a delicate balance between Earth's gravity and the centrifugal force of its orbital motion. But when an external force, the gravity of the black hole, began to interfere with this balance, the moon's orbit would become destabilized. At first, the changes would be small. The moon would begin to move along a slightly different trajectory. Its orbit would become more elliptical. But as the gravitational influence of the black hole strengthened, the moon could either move away from Earth or, conversely, begin to approach us. In the worst case, it could be completely torn from orbit and sent on its own journey to the black hole. What's interesting is that these effects are related to so-called tidal forces. Tidal forces are the difference in gravitational attraction between the near and far sides of an object. On Earth, we observe tides in the oceans precisely because of the tidal forces of the moon and Sunday. But the tidal forces of a black hole would be on a completely different level. At a distance of several million kilometers from the black hole, these forces would begin to affect Earth. The side of the planet facing the black hole would experience stronger gravitational attraction than the opposite side. This would create tension, tending to stretch the planet along a line directed toward the black hole. On Earth, we would begin to observe strange and disturbing phenomena. Ocean tides would become extreme and unpredictable. Normally, tides caused by the moon and sun raise the water level by several meters. But now the black hole would add its contribution, creating tidal waves of unprecedented force. Coastal cities would be under threat. Water would rise tens of meters, flooding low-lying areas. But these would not be ordinary tides that predictably come and go. The gravitational influence of the black hole would create chaotic, unpredictable changes in water level. Navigation systems would begin to malfunction. Modern civilization relies on GPS satellites that use extremely precise calculations based on general relativity. These satellites account for the fact that time flows slightly slower in the stronger gravitational field on Earth's surface compared to satellite orbit. But the presence of the black hole would introduce additional gravitational distortions that were not accounted for in the algorithms. GPS coordinates would begin to drift and become unreliable. Communication with spacecraft would become difficult. Radio signals that we send to our probes and receive from them propagate in straight lines through space. But the curvature of space-time around the black hole would bend the trajectories of these signals, causing delays, distortions, and loss of communication. Astronomers would observe increasingly dramatic effects in the sky. Stars would begin to move from their familiar positions due to gravitational lensing. Entire constellations would be distorted beyond recognition. The black hole would dominate the sky, a huge dark area surrounded by a distorted, pulsating ring of light. But all this would be only a prelude. The real nightmare would begin when we approached even closer to the black hole. Let's continue our journey into the abyss. Now let's imagine that Earth is at a distance of about 1 million kilometers from the black hole. To understand the scale, this is approximately 2.5 times greater than the distance from Earth to the moon. Sounds like a safe distance, doesn't it? But for a black hole, this is already dangerously close. At this stage, tidal forces would reach such power that they would begin to literally tear our planet apart. Imagine giant invisible hands pulling one side of Earth toward the black hole, while the other side remains behind. The planet would begin to deform, stretch, lose its perfect spherical shape. The first and most catastrophic consequence would be earthquakes. But these would not be ordinary earthquakes that we have, unfortunately, become accustomed to. These would be seismic events with a magnitude exceeding everything ever registered in human history. Earth's crust, the thin shell of solid rock on which we live, would begin to crack. Tectonic plates, which normally move slowly at a rate of several centimeters per year, would suddenly begin to shift at terrifying speed. Faults would widen, new giant cracks would appear, stretching for thousands of kilometers. Mountain ranges that had been forming for millions of years would begin to collapse. The Himalayas, the Andes, the Rocky Mountains, all these majestic mountain systems would split and crumble. Valleys would fill with debris, and in place of plains, New mountains would rise from crumpled Earth's crust. Cities would turn into ruins in a matter of minutes. Even the strongest buildings designed to withstand earthquakes would not stand against such forces. Bridges would collapse, roads would split, communications would be destroyed. Modern civilization, dependent on complex infrastructure, would collapse. But earthquakes would be only the beginning. Beneath Earth's crust is the mantle, a layer of hot viscous rock that slowly circulates due to convection currents. The tidal forces of the black hole would disrupt this fragile equilibrium. The mantle would begin to move chaotically, creating enormous pressure on the crust from below. This would lead to unprecedented volcanic activity. Volcanoes that had slept for millennia would suddenly awaken. New volcanoes would form in places where they had never been. Eruptions would occur simultaneously around the world, in Iceland and Indonesia, in Italy and Kamchatka, in Yellowstone, and on the ocean floor. Imagine hundreds of volcanoes erupting lava, ash, and poisonous gases simultaneously. The sky would darken from volcanic ash. Ash particles would rise into the upper layers of the atmosphere and spread across the entire globe, blocking sunlight. The temperature on the surface would begin to drop sharply, an effect similar to volcanic winter. But simultaneously with this cooling, heating would also occur. Lava flows would cover huge territories. Entire regions would turn into scorching wastelands. Forests would catch fire, creating giant fires that would add even more smoke and soot to the atmosphere. The oceans would behave completely insanely. The tidal forces of the black hole would create giant waves, tsunamis hundreds of meters high that would roll across the planet. These waves would not be like ordinary tsunamis caused by earthquakes. They would be caused by direct gravitational impact of the black hole on ocean water. The coastline would change beyond recognition. Coastal cities would be washed away. Entire islands would disappear underwater. But even stranger, in some places the opposite would occur. Sections of the seabed would rise above the surface due to deformation of Earth's crust. New islands would appear where before there was only water. Earth's atmosphere would also begin to behave strangely. Air is also matter, and it is subject to gravity. Tidal forces would affect not only the solid and liquid parts of the planet, but also the gaseous shell. Atmospheric pressure would begin to fluctuate unpredictably. Winds of incredible force would begin to blow across the entire planet. These storms would make the most destructive hurricanes in Earth's history seem like a light breeze. Wind speed would reach hundreds of kilometers per hour. These hurricanes would destroy everything in their path. Buildings, forests, even the Earth itself, lifting tons of dust and debris into the air. Earth's magnetic field, which protects us from cosmic radiation, could also begin to fluctuate. This field is generated by the movement of molten iron in Earth's outer core. But if the mantle and core begin to move chaotically due to tidal forces, the geomagnetic field may weaken or even temporarily disappear. Without this protection, streams of charged particles from the sun and cosmic rays would begin to bombard the surface, posing a deadly danger to all living things. What would happen to life on Earth at this stage? The prospect would be extremely bleak. The combination of earthquakes, volcanic eruptions, tsunamis, extreme weather conditions, and possible increased radiation would make most of the planet's surface absolutely uninhabitable. Plants would die due to lack of sunlight blocked by volcanic ash. This would lead to collapse of food chains. Herbivorous animals would lose their food, then predators would follow. Oceans would be covered with a layer of ash. which would disrupt marine ecosystems. Plankton, the foundation of marine life, would die, leading to mass extinction of marine species. Human civilization, as we know it, would collapse. Cities would be destroyed, infrastructure annihilated, agriculture impossible. Survival will be possible only in the most protected places, perhaps in deep underground shelters where people could hide from earthquakes, have supplies of food and water, and be protected from radiation. But even in such shelters, chances of long-term survival would be small. Resources would eventually run out, and the surface would remain deadly dangerous. And most importantly, our planet would continue to approach the black hole. Let's continue our thought experiment and see what would happen if Earth continued its fateful journey. The culmination of this cosmic tragedy awaits us ahead. As Earth approaches the black hole even closer, say, to a distance of several tens of thousands of kilometers, we enter the final phase of our scenario. Here, tidal forces reach such power that the planet's structure itself can no longer resist. There's a critical point in space called the Roche limit. This is the distance at which tidal forces from one object become stronger than the other object's own gravity holding it together. Inside the Roche limit, an object begins to tear apart. For Earth approaching a black hole with a mass of 10 solar masses, this limit would be approximately 18,000 kilometers from the event horizon. As soon as our planet crossed this invisible boundary, an irreversible process of its disintegration would begin. But let's first understand a scientific term that has become almost legendary in describing black holes: spaghettification. Yes, this is a real scientific term, and it describes exactly what it sounds like. Spaghettification is the process by which an object is stretched into a long, thin form resembling spaghetti due to the difference in gravitational force between the near and far ends of the object. Gravity obeys the inverse square law. It decreases proportionally to the square of distance. This means that if you're twice as close to a black hole, the gravitational force is 4 times stronger. Now imagine Earth approaching a black hole. The side of the planet facing the black hole is approximately 12,742 kilometers closer than the opposite side. This is Earth's diameter. At such close distance to the black hole, this difference creates an enormous difference in gravitational attraction. What would happen when Earth crossed the Roche limit? The process would be terrifyingly impressive. Our planet would literally begin to fall apart into pieces. First, Earth's crust would split into huge fragments. These fragments, the size of continents, would begin to tear away from the planet, stretching toward the black hole. Imagine Eurasia or America tearing away from the rest of the planet and beginning its own journey to the event horizon. The mantle, located beneath the crust, would no longer be held by the solid shell. This hot, viscous rock would begin to flow outward like the contents of a burst balloon. Streams of molten rock at temperatures of thousands of degrees would scatter in all directions, though most of them would be inexorably drawn to the black hole. The oceans would evaporate almost instantly. The extreme heat from the hot mantle and friction caused by tearing forces would turn water into steam. This steam would mix with the atmosphere, which itself would be rapidly escaping into space, torn from the planet by tidal forces. Earth's core, the densest part of our planet, consisting mainly of iron and nickel, would hold out the longest. But even it could not withstand the monstrous force of the black hole. As the surrounding layers tore away, the core would remain intact for some time, like the last bastion of the planet's integrity. But ultimately it too would begin to deform, stretch, and break into pieces. This entire process would take relatively short time, perhaps several hours or even minutes, depending on the exact distance and approach speed. Earth, a planet that existed for more than 4.5 billion years, that witnessed the emergence of life, the evolution of millions of species, the birth and fall of civilizations, would turn into a cloud of debris stretched in a spiral around the black hole. This debris would begin to form an accretion disk, one of the most impressive structures in space. An accretion disk is a spiral formation of matter rotating around a black hole at enormous speed. Let's look in more detail at what happens in this disk, because here physics becomes truly extreme. As Earth's debris moves inward in a spiral, it accelerates. Speeds become incredible, a significant fraction of the speed of light. At such speeds, friction between particles of matter becomes phenomenal. Imagine billions of tons of rock, metal, and other materials rubbing against each other at near light speeds. This friction generates a monstrous amount of heat. Temperature in the accretion disk can reach millions of degrees Celsius, hotter than the surface of most stars. At such temperatures, ordinary matter cannot exist in familiar form. Molecules are destroyed, atoms are torn apart, electrons are torn from nuclei. What was once Earth, rocks from which mountains were made, ocean water, iron from Earth's core, turns into plasma, the fourth state of matter. In this plasma, protons, neutrons, and electrons exist separately, forming hot ionized gas. And this plasma glows. Oh, how it glows! The accretion disk around a black hole becomes a source of incredibly powerful radiation. It shines in X-ray and even gamma ranges, the most energetic forms of electromagnetic radiation. If someone could observe this from a safe distance, they would see a blindingly bright disk surrounding the absolutely black shadow of the black hole. In fact, accretion disks around black holes are among the brightest objects in the universe. Quasars, ultra-bright objects in the centers of distant galaxies, are precisely supermassive black holes with massive accretion disks. Material from the destroyed Earth in the accretion disk would radiate so much energy that it could be seen from other star systems. Irony of fate. In its death, our planet would become the brightest beacon in space, albeit briefly. But radiation is not the only amazing phenomenon in the accretion disk. Magnetic fields play a critical role here. Moving charged plasma generates powerful magnetic fields that twist and intertwine in complex structures. These fields can accumulate enormous amounts of energy. Sometimes these magnetic fields suddenly reorganize in a process called magnetic reconnection, releasing colossal amounts of energy in the form of flares. These flares create powerful streams of particles and radiation that burst out from the disk. An even more impressive phenomenon is the formation of jets or relativistic outflows. Part of the matter from the accretion disk does not fall into the black hole, but is ejected in the form of narrow beams along the rotation axis of the black hole. These jets move at a speed close to the speed of light and can extend for thousands of light years into space. The mechanism of jet formation is not fully understood, but it is believed that magnetic fields play a key role, twisted by the rotation of the black hole and accretion disk. These fields act as a giant particle accelerator, shooting matter into space with incredible energy. Imagine particles that were once part of Earth, atoms that perhaps were in your body or in the body of a dinosaur millions of years ago, are now rushing through the galaxy at near light speed. Some of these particles could travel thousands of light years before they collided with interstellar gas or other objects. But the overwhelming majority of Earth's matter would await a different fate. As material continues to spiral inward, it approaches the point of no return, the event horizon. Let's now follow a particle of matter, perhaps a carbon atom that was once part of a living organism on Earth, on its final journey beyond the event horizon. The event horizon is not a physical wall or barrier. If you approached it, you wouldn't see a warning sign, point of no return. It's simply a boundary in space-time, a mathematical surface where escape velocity becomes equal to the speed of light. For an observer located far from the black hole, something strange happens. As matter approaches the event horizon, it appears to slow down. Time near a black hole flows more slowly due to gravitational time dilation, an effect predicted by Einstein's theory of relativity. Light emitted by falling matter is stretched. Its wavelength increases, shifting toward the red end of the spectrum. This is called gravitational redshift. Matter becomes increasingly dim and red. From the perspective of a distant observer, it never fully reaches the event horizon. It seems to freeze at the very edge, becoming infinitely dim but never crossing the final boundary. But this is just an illusion caused by relativistic effects. From the perspective of the falling matter itself, everything happens differently. For it, crossing the event horizon occurs in finite time and quite quickly. What happens when matter crosses the event horizon? Here we enter territory where our understanding of physics becomes incomplete, but we can make some reasonable assumptions. Inside the event horizon, the roles of space and time seem to swap places. Outside, you can move in space in any direction, but time flows only forward. Inside the event horizon, the direction toward the singularity becomes not a direction in space, but a direction in time. Movement toward the singularity becomes as inevitable as the flow of time. The time from crossing the event horizon to reaching the singularity depends on the size of the black hole. For our stellar black hole, this would take fractions of a second. For a supermassive black hole in the center of a galaxy, hours or even days. As you approach the singularity, tidal forces become ever stronger. Even atoms begin to tear apart. Protons and neutrons in atomic nuclei are destroyed into their constituent quarks. The very fabric of matter breaks down into elementary particles. And then comes the encounter with the singularity, a point of infinite density at the center of the black hole. Here, all known laws of physics cease to work. General relativity predicts that at the singularity, the curvature of space-time becomes infinite, but physicists believe this indicates the limit of the theory's applicability. In reality, at such extreme scales, quantum effects should manifest, and we need a theory of quantum gravity, which we don't yet have, to understand what really happens. Some theories suggest that the singularity may not be a point, but something more complex. Others suggest the possibility of white holes, or even new universes being born inside black holes. But whatever the final answer, the practical result for Earth's matter is one. It disappears forever from our universe, adding its mass and energy to the mass of the black hole. Now, after we've gone through this apocalyptic scenario from beginning to end, let's return to reality and ask an important question. Could this actually happen? How much should we worry about encountering a black hole? Great news. The probability of such an event is practically zero. Space is huge, so huge that it's even hard to imagine. Distances between stars are measured in light years, and black holes, though there are many of them in the universe, are distributed at colossal distances. The nearest known black hole to Earth is at a distance of about 1,000 light years. This means that even moving at the speed of light, the fastest speed in nature, it would take 1,000 years to reach it. Its gravitational influence on our solar system is completely negligible, immeasurably small. Black holes don't hunt for planets. They don't roam the galaxy in search of victims. They move in predictable orbits around the galactic center, just like our sun and billions of other stars. For Earth to encounter a black hole would require an incredible, almost impossible series of events. First, something would have to knock Earth out of its orbit around the sun. This in itself is extremely unlikely. Then Earth would have to accidentally head in exactly the direction where a black hole is located, which in the infinity of cosmic space would be an incredible coincidence. And finally, trajectories would have to coincide with accuracy sufficient for catastrophic approach. The mathematical probability of all these events occurring simultaneously is so small that we can confidently say, this will not happen. Moreover, even the supermassive black hole at the center of our galaxy, Sagittarius A-, is at a safe distance of about 26,000 light years. It poses no threat to us. Our solar system revolves around a galactic center in a stable orbit and will continue to do so for billions of years. However, black holes do pose a danger to some cosmic objects. In dense regions of space, such as galactic centers or star clusters, where star concentration is higher, the probability of collisions and close flybys increases. Astronomers have observed events called tidal disruption of stars. This occurs when a star comes too close to a supermassive black hole and is torn apart by tidal forces, exactly as we described for Earth. Material from the torn star forms a bright accretion disk, creating a sudden burst of radiation. These events have been observed in other galaxies using telescopes. They manifest as sudden bursts of X-ray and ultraviolet radiation from galactic centers. Studying these events helps scientists better understand the physics of black holes and test theories of gravity in extreme conditions. There is also the theoretical possibility of rogue black holes, objects ejected from their galaxies as a result of gravitational interactions during galaxy mergers. Such rogue black holes could travel through intergalactic space. But even if such a black hole entered our solar system, which is incredibly unlikely, we would detect it long before it became a threat. How? By its gravitational influence on the orbits of planets, asteroids, and comets. Gravitational perturbations would be noticeable years or even decades before dangerous approach, giving us enough time for, well, honestly, we could do little against a black hole, but at least we would know about the impending catastrophe. So while Earth's encounter with a black hole remains in the realm of science fiction, this thought experiment teaches us much. First, it demonstrates the incredible power of gravity in its extreme manifestations. On Earth, we take gravity for granted. It keeps us on the surface, makes objects fall. But near a black hole, gravity becomes a force capable of tearing apart planets, destroying atoms, and distorting space and time itself. Second, we see how Einstein's theory of relativity, developed more than a century ago, predicts these extreme phenomena with astonishing accuracy. Time dilation, space curvature, gravitational lensing, event horizon. All these concepts that seem so abstract and far from everyday life become critically important near a black hole. Third, this scenario shows us the fragility of our existence. We live on a small planet, in a narrow range of conditions that makes life possible. Small changes in temperature, in atmospheric composition, in gravitational environment can make Earth uninhabitable. This is a reminder of how important it is to protect our planet and environment. But at the same time, contemplating black holes and extreme cosmic phenomena expands our understanding of what's possible. The universe is full of wonders and horrors that exceed our imagination. Black holes are not just destructive monsters. They are also natural laboratories where matter and energy behave in ways we are only beginning to understand. Studying black holes has helped us solve many cosmic mysteries. We learned that supermassive black holes play a key role in galaxy evolution. Their gravitational influence and energy released by accretion disks can trigger or stop star formation in a galaxy. We also learned about gravitational waves, ripples in the fabric of space-time, created by black hole mergers. These waves, first detected in 2015, opened a completely new window into the universe, allowing us to hear cosmic events we cannot see. Black holes also make us think about fundamental questions of physics. What happens to information that falls into a black hole? This is the black hole information paradox, which is still not fully resolved. Do other universes exist inside black holes or connected to them? How can we unify general relativity and quantum mechanics to describe the singularity? These questions are at the forefront of modern physics, and answers to them could revolutionize our understanding of reality. We have taken an incredible journey, from the first alarming signs in the starry sky to the final plunge beyond the event horizon. We have seen how our home planet deformed, split, tore apart, and turned into a stream of hot plasma before disappearing forever into one of the most mysterious objects in the universe. Although this scenario remains theoretical and, fortunately, extremely unlikely, it shows us the scale and power of natural forces in space. The universe is full of extreme phenomena: exploding stars, colliding galaxies, jets of matter moving almost at the speed of light, and of course black holes, where gravity reaches its limits. Every time we look at the night sky, we see a relatively calm picture. Stars twinkle, planets move in their orbits. Everything seems orderly and predictable. But this is only because the most dramatic events occur at enormous distances or on timescales that exceed human life. Somewhere out there, in the depths of space at this very second, a star may be being torn apart by a black hole. Two black holes may be merging, creating gravitational waves that spread through the universe. Matter may be falling beyond event horizons, disappearing from our reality forever. And all this happens according to the laws of physics that we have discovered and continue to explore. This is one of humanity's greatest achievements: the ability to understand these extreme phenomena even without the ability to observe them directly, using mathematics, observations, and brilliant theoretical ideas. Black holes remind us that the universe is much stranger, more amazing, and more grandiose than we could imagine. They challenge our intuition, expand the boundaries of our understanding, and inspire us to continue exploring space. So next time you look at the starry sky, remember, somewhere out there, among those twinkling points of light, hide objects so extreme, so powerful that they can tear apart planets, distort time and space, and keep secrets we're only beginning to unravel. Thank you for being with us on the QUASARIA channel. If you enjoyed this journey to the edge of the abyss, don't forget to put a like and subscribe to the channel. Click the bell to not miss our new episodes about the mysteries of space. In the comments, tell us what cosmic catastrophes or amazing phenomena you would like us to analyze in the next videos. Maybe galaxy collisions? Or what happens inside a neutron star? Or maybe a journey to the edge of the observable universe? Remember, although black holes seem frightening, they're also some of the most exciting objects to study. They show us what nature is capable of in its extreme manifestations and remind us that there is always something new to discover in space. Until new meetings in the expanses of the infinite universe. This was the QUASARIA channel, and we will continue to explore the most amazing mysteries of space together with you. Take care of yourselves and our beautiful planet, because as we confirmed today, it really is special